Hello everybody and welcome back to Chem Talk, where today we'll be talking about isothermal expansion and compression. Now, the first question is, what is an isothermal process? So during a process of a reaction in an isothermal state, the temperature stays constant. So this means that there's a transfer of heat and it is very slow, which allows the system to stay at thermal equilibrium. Basically, the thermodynamics do not change while this reaction is taking place. We can kind of see this when we look at a fridge. Now, a fridge works isothermally. The mass inside, the pressure, and the volume are all constantly changing, but the temperature inside the fridge seems to always stay at the same temperature. So this means that the heat in to the fridge equals the heat out of the fridge, which allows our food to stay the same temperature every single day, all day. So how does this relate to compression? What is isothermal compression? So isothermal compression is the reduction of volume by keeping the temperature constant throughout the process. The work of compression is converted into heat, but the system has to reject some of this heat. In order to keep the temperature constant, some heat is absorbed while some heat is not absorbed at all. And this also means that when this heat is absorbed, the same of heat absorbed equals the same amount of heat that is released, which allows the temperature to stay constant. Now we're going to look at our perfect gas law, or our ideal gas law, whatever you know it as, which is PV equals nRT. Now, since our number of moles, or mass, R is a constant already and temperature is held constant, we can see that the only variables changing in our ideal gas law is PV. And from this, we can actually directly connect Boyle's law to our isothermal compression, which is P1 V1, or our conditions before, equal P2 V2, or our conditions after a reaction takes place. Now, what is isothermal expansion? Obviously, isothermal expansion is the exact opposite of isothermal compression, which is where the volume increases while the temperature still stays constant. This expansion can occur in a vacuum or it can occur in a closed state. Please note that a vacuum is not the same thing as a closed system. An isothermal expansion is also related to Boyle's law because the only variables changing are the volume and pressure. Again, we see the temperature stays the same, so we can continuously use Boyle's law in order to find what the isothermal expansion actually is. Now, after I've mentioned Boyle's law a couple of times, we're going to do an example with Boyle's law. So on the screen right now, you're going to see the example, a balloon filled with pure O2 at temperature 800 Kelvin with 2 moles in it was compressed from 4 liters to 2.5 liters. What was the initial pressure and what is the pressure after the compression? Now, there are 2 parts of this question. First, we're asked to find our initial pressure, and then we're asked to find our final pressure. So for our first part, we're going to solve for the initial pressure using our perfect gas law. We're going to be able to use our perfect gas law because we want to note that in the problem itself, we see that it is only pure O2. We also want to note that unless stated, we are going to say that our gases act ideally because of the kinetic molecular theory of gases. Now we're going to be able to isolate our only variable that we don't know, which is P, and in order to do that, we're going to divide both sides by V, and we're going to see that P equals nRT over V. So this means we have our 2 moles, which is mentioned in the problem, our 8.31451, which is actually our value of R, which should always be given to you, or if not, it should be tattooed onto your brain at this point. We also have our temperature, which is 800 K, and then we divide all of that by 4, which is our volume. And we're going to see that our pressure is 3,325.804 atm. Now you're going to see that this 4 down here is actually subscripted. And I'm going to put this here for now because we want to make sure that we have no rounding errors at the moment, but this 4 is not one of our significant figures. Our significant figures is only over 2 decimal points. This is not significant, which is why it's going to go in a subscript. The next part of this problem is to use Boyle's law to find the final pressure. Now, Here we're going to use Boyle's law in order to find our final pressure, which is P1 times V1 equals P2 times V2. In order to isolate our variable, we are going to divide both sides by V2, and we're going to find that P2 equals P1 over V1 divided by V2. Now we're going to just plug in our values. So we're going to find that our initial pressure is going to be what we found in the previous part. And then our initial volume is 4.00 liters. And then we're going to also plug in our final volume, which is 2.50 liters. After doing the math, of course, you're going to do the top first, then you're going to do the bottom. We find that our pressure is 5,321.29. Here, our 0.29 has actually been rounded, and here you can see that we only have 2 decimal places and that there is no subscript, because that is the amount of significant figures that we have. If we had more decimals, it would actually not be accurate at all, because anything beyond these 2 decimal points is actually not certain. We wouldn't be able to justify them being there because we've only been given 2 decimal places.